Okay, welcome to the notes for velocity and acceleration. We've gone over speed and velocity at this moment, and we're going to really talk today about acceleration. What is acceleration? To understand that, we have to start with what velocity is, how velocity is different than speed. All right, so velocity is a vector. It's a vector quantity, so it requires a direction. So example is you are traveling at 12 meters per second to the right. Okay, another one could be you are going 1.7 meters per second up. As long as there's a direction, then that is, by definition, a velocity. Now, most of the time, we're going to be talking about straight line motion, whether it be left, right, up, down, sideways, whatever. And for the most part, we will forget to put in the direction. It's not that important. But you do have to understand that there is a difference if someone says that there's 12 meters right, 12 meters per second left is different than 12 meters per second right. That's a different velocity because of the direction. That's what we're trying to get at. All right, the simple way to think of velocity is that it is speed with direction. And as we looked at distance and displacement, we see that the difference really is the fact that velocity uses displacement and speed uses distance. And there can be a difference in the same travel. There can be a difference between your distance and your displacement. But again, since once we've left that definition, as we work with things, we always work with things in straight line unless we are doing changing motion, changing direction. So we'll just keep it pretty simple from here on out. All right, now acceleration. What is acceleration? Acceleration is also a vector quantity, so it also requires a direction. So example, it can be 3.5 meters per second squared to the right. Or it could be something like negative 2.7 meters per second squared. Negative implies that it's either going left or going down, the acceleration. And again, with everything else, as we proceed, we are mostly going to do things only in a straight line, and so we will not have to worry too much about the direction. We'll just put positives and negatives in there. All right, our definition of acceleration is the change in velocity divided by time. But how does that look like in format? Usually in an equation format, you see it as VF minus VI over the time. You do need to use parentheses because if you don't, then it will divide the VI minus T and then subtract that from VF. What does VF mean? VF is your final velocity. It's what you're doing at the end. And VI is your initial velocity. And your initials are the first letters of your names, of your name. So initial means is beginning, start, first, stuff like that. Whatever your initials are your first letters of your name, so initial means first. So it's whatever you're doing at the beginning. Now, it doesn't mean that it's the first speed that shows up in a word problem. It means what in your travel, as you're reading a word problem, you have to figure out what's going on in the sentence. You have to see a picture in your eyes, in your head, about what it is that's going on. So here we go. We have a skateboard traveling 7 meters per second and accelerates to 21 meters per second down a hill in a time period of 4.5 seconds. So if he's traveling 7 and then accelerates to 21, 7 is your VI, 21 is your VF, time is in seconds. Write your equation down. A equals VF minus VI over T. 21 minus 7 divided by 4.5. Then you'll put that in your calculator, and you get 3.11 meters per second squared. Grab your calculator and make sure you can use it. Make sure that you put the parentheses in there. If you get something like about 19 or 20, that means you didn't put the 21 minus 7 in your calculator, because it's going to do 7 divided by 4.5 and then subtract that from the 21 if you don't use parentheses. So make sure you use parentheses, or you can hit 21 minus 7, enter, divide by 4.5. Whatever works for you. It's your work. You just have to get it right. All right, using these dots, you can see this as an example of how to see speed or acceleration. The dots represent a constant time. There is a ticker that is going up and down, and then you pull this tape through, and it puts a dot on the tape for your movement. So if you're looking at these things and the distance is the same, then that's a constant speed, because the time is constant. It's just a tick. I'm going to make a little sound here. It's just a tick going. So the ticks occur at an even rate, so the time is constant. So if the distance between the two is the same, then that means the speed is the same. If the distance changes between the dots, then that means you're changing your speed. So look at the one on the right. We start off, their dots are on top of each other, and then the distances start getting further and further and further apart. So if you know the sequence of the tap, 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 then you can actually figure out the speed of this particular stuff. So this is a way to reference and show acceleration and not have to have a word problem. Okay, so some questions on the back. So what you could do is see how much we understand here. All right, acceleration, yes or no? Now remember, acceleration, this is another way to think of velocity, is speed with a direction. Speed with direction. And acceleration is the change in velocity over time. The triangle means change, the change in velocity over time. So if we are at constant velocity means we're going the same speed in the same direction, so we are not accelerating. If I'm going 5 meters per second, then I'm going 3 meters per second, a change in speed means that my velocity has to be changing, because velocity is made up of both speed and direction. So if I change speed, it's easy. Yes, that's acceleration. A car going around a corner. Over here, the car is going 10 meters per second, and it's still going 10 meters per second after it turns, but it changed direction. So that is acceleration. Constant speed. Okay. Velocity is speed with a direction. So if my speed is constant, I'm not accelerating using my speed, but as we see in this picture, my speed doesn't change with the car, but it changes direction. So constant speed is a maybe. I can be going the same speed but be turning and have acceleration. You can see this when you're in your car and you feel the motion. If someone takes a sudden left turn, doesn't change speed, you're going to be thrown to the right in the car is what it feels like. That movement that your body feels is acceleration. If you're stopping, you're changing speeds, so that means yes, that there is acceleration. If you're at rest, there is nothing going on, so we have no change in our acceleration or our velocity. All right, we won't worry too much about these down here, but let's just break down what these dots mean. Are these dots getting the same distance, a closer distance, or a farther distance as you go left to right? They're getting closer and closer. That means that this car is slowing down, so we have a negative acceleration. Negative acceleration means that you are slowing down. All right, object B, the dots are getting farther and farther apart. That means we have a positive acceleration. Object C, the dots are the same distance apart all the way through, so we have zero acceleration. And here we have a constant speed because the dots are the same distance between each other. But we have a change in direction. That means we have a change in velocity and we have acceleration because we're curving. We're changing the direction of our motion, but we're staying the same speed. That means we do have acceleration. All right, let's do some math problems. Okay, just some simple little math problems. We have a cheetah that is at rest and accelerates to 19 meters per second in 2.3 seconds. All right, the cheetah is at rest and accelerates. At rest means that you're not going anywhere, so your VI is 0. That makes your VF the 19, and 2.3 is your time. We plug it into our acceleration formula, VF minus VI over T. We end up with 19 minus 0 over 2.3. Again, you have to use parentheses or you'll get 19. And that particular answer is 8.26 meters per second squared. Okay, where did we get this meters per second squared? Well, on the top, let me put this with a different color here. We have meters per second, and we're dividing it by seconds. Sometimes you'll hear someone say this is meters per second per second. Using algebra, if you have a meters per second on top, you can bring that other second down to the bottom, and we'd have meters per second times seconds, like this, and that's where we get meters per second squared. Again, you'll often hear it called meters per second per second. A car is traveling 45 miles per hour when it accelerates to 75 miles per hour in 3.5 seconds. Okay, in America, we use miles per hour as our speed, where cars are. If you go to purchase a car, we're traveling at 45 miles per hour, that's VI, and then we accelerate to VF. So if you purchase a car and you look at the information on the car, you'll actually find that they give the information acceleration in what they call miles per hour per seconds. So we wanted to show you a couple of these. All right, you put this in your calculator. And you get 26.5 miles per hour per second. So if you're out looking at cars online, because most of you are juniors, so it's time to start thinking about cars, you'll actually look up the acceleration rate of different cars, and they'll give you the acceleration in miles per hour per second. We have a runner moving at 3.5 and increases his speed to 7.4 over 5.1 seconds. So VI, VF, and T. Notice that we're writing the equation down each time. We're doing that to kind of get repetitive, so you get used to the equation. You are required to always show your work, which means you have to do this part where you write in the numbers before you put them in your calculator. I don't care how great you are with a calculator. If you don't show your work, you miss the problem. 7.4 minus 3.5 divided by 5.1, 0.76 meters per second squared. So you do have to pay attention to what our units are. If our velocity is in meters per second and our time is in seconds, we're going to do meters per second squared. We're only going to go back and forth between meters per second and miles per hour on the speed on these worksheets. And occasionally, if you go to Europe or a country that uses the metric system, their speed limits are not in miles per hour, they are in kilometers per hour. And all speedometers since the late 70s have used, you've got a kilometers per hour also on your speedometer if it's an analog, something that shows up on a screen. All right, a train is traveling at 34 meters per second, and it's going to slow down to 15 meters per second over 15 seconds. So determine the acceleration. Okay, so we have acceleration. 34 is our VI, 15 is our VF. Notice that our VF is smaller than our VI, and that means we're going to have a negative acceleration, which is what happens when we slow down. So 15 minus 34 over 15. That gives us a negative 1.27 meters per second squared. All right, so that's how you solve simple acceleration questions. We didn't have you solve for VF or VI or the time or anything like that. That's just an algebraic manipulation to let you move the things around. So we'll have some practice worksheets and do some activities if you're in class. So good luck with this stuff. Pay attention, write your information down. Calculators will do everything you tell them to do, and sometimes we tell them to do the wrong thing. So write down what you're going to do and then put it in your calculator. Good luck, guys.